what I want to give you today, because I know that some of the people in the audience know a lot more about the physics, and some of them are from outside the core high energy nuclear physics. So I thought I would give a mix of the two, because there are some detailed talks coming up afterwards, which we can be used for discussions in the afternoon. But it is really important for this project to get broader community informed about what's going on and what are we expecting to happen in the next 10 years. So I thought I would mix the science with the issues that are coming with the science. So if you remember, the electron ion collider physics was summarized in this No, it's stuck. It's got the recording. Oh, now it should work.
Click on the slide again. Make sure you're on the right program.
Yeah. So the EIC science was summarized in something that looks blue, but was called the EIC white paper. That was prepared for the long range plan in 2015. That made the case finally after about 15 to 20 years of activity on this field.
Sorry, I think the people at home can't see your slides. We're not sharing it yet. Sorry about that.
Yeah,
the program will work. Let's see.
Yeah, that's the square. That's good.
That.
Yeah, good. And then you can minimize this part. Good. That one should also go. We can go to the more video. Yeah, good.
Okay. You're not actually sharing the presentation.
Ah, see, it's not sharing it. Okay.
Once you click slideshow, it opens a new window, and then so
what I thought. So we should share the.
Can you just share the whole screen?
Yeah, just
Yeah, that's the idea. Where is it?
It's the top.
It's
already selected.
Yeah.
Desktop one. Okay.
Sure.
That looks better. So
okay.
Sorry for the interruption.
That's all right. And that then became, after 20 years of a lot of work from many people, became the white paper, and then eventually got in with the long range planning, the final document that resulted from it, that said the physics of the EIC was broadly supported by the Nuclear Science Advisory Committee. That was followed by a year-long study by the National Academy of Sciences, which reported in 2018, July, a consensus report that said that the science was good enough to go forward. And that resulted in an internal friendly competition in the EIC community led by Jefferson Lab proposal and a Brookhaven National Lab proposal. After a DOE external evaluation, it was decided that the machine would be built at Brookhaven using the RIC complex. That resulted, the next step, the user community came back together, which had proposed the science to come back with these parameters of the machines to come up with a detector. This happened all throughout the pandemic. So we were all working at home through these 2 years, but that was prepared. And I'll go back in a little bit more detail into that. So that's the current status of it. I want to be very clear that this happened in the last 5 years, but there was a critical meeting that happened here in 2009 to 2010. There was a program on EIC science I thought was the biggest impactful study that really brought all the science of EIC together that had happened over the last 15 years before that, and really made us go through the science that eventually made the case. So I'm really, I remember I was here for, like you, for 5 weeks or 4 weeks. You've been better than that, but it was a 5-week program, but we were here continuously working on this. And it was really important that INT played a very important role in the science of EIC at the beginning, making the case. Now, title on the page says Electron Ion Collider Science, and I have turned it into why, how, and when. Added to that. That's my change. So the way this talk will go, I will talk about the higher level review of EIC science, which includes the core physics that was mentioned in the EIC white paper. And I will not go into details. I'll just refer to many talks that have happened, are happening this week, and some of them were already in the past. And then I will go into the accelerator beyond the science of the EIC, beyond the core physics. Then I will talk about the EPIC detector, which was collaboration that just formed. And then I will talk about the detector 2, the potential for second detector, which is intimately connected to the science of EIC beyond the core physics. So there should be some complementarity in it and some re-emphasis on certain important measurements. So those are the kind of discussion that are just about to start. And I will give you a brief overview of what's that and finalize with the timeline, etc. Now in QCD, in the partonic, the next level that compared to the things that we were talking about, we talk about parton densities and resolution, how we look at it. So this is a very broad summary of what we like to do in QCD and nuclear physics. What is plotted on the x-axis is 1 over Bjorken x, which is proportional to the parton density. And what is plotted on the y-axis is the Q squared, that's the resolution. And of course, we all know there is a strong coupling, a non-perturbative regime, and somewhere it changes into a perturbative regime and goes into very high Q squared, where the resolution is extremely well understood. So that QCD at extremely high Q squared with weakly correlated quarks and gluons is well described by perturbative QCD. As against that, there is a nonlinear regime. Below the non-regime, there is this region which we call the hadrons, looks more like that. Symbolically, in pions, it might be 2 quarks, and it is strongly in the non-perturbative regime where calculations are difficult and challenging. And this is where the hadron structure emerges. There are regions which we want to systematically understand and explore using not just the electron ion collider, but any technique and tool that we have at our disposal. Proton-proton collisions, nucleus-nucleus collisions, electron-nucleus and electron-proton collisions with polarization and not, to understand how these transitions happen smoothly in the QCD that we are trying to understand. And then there is this regime of high-density gluon matter so this is the high-density gluon matter, but if we can push this in the perturbative regime, there are calculations made, led by people who were associated with the center for a long time, like Larry, who have observed that you can actually, if you can reach this region of high-density gluonic matter or partonic matter in the weak coupling regime, that would be an interesting place where gluon dominates the nucleus or the proton, and they have proposed very interesting properties of such material. They've called it color glass condensate, and such are the things that we want to study overall. We need precision and control to do that. And I believe that the electron ion collider, with its method, the deep inelastic scattering, where you probe QCD, which is the unknown, with an electroweak probe, the precision of well understood electroweak probe comes into picture. So this is the reason why precision and control is needed to explore all of this. So while we were here, we identified from all this activity that I mentioned in the broad X and Q squared and resolution range, we identified 3 high-level topics to make the case for the EIC. And not because nobody else could do it, but if we believe strongly that if at all these topics are to be studied in detail, this is the machine to do it. No other machine will be able to do it as well as this electron ion collider can. There were other interesting things that could be done with the EIC, and I will mention them later, but these are the things that we based our case on. We also had to be mindful of the fact that this machine was primarily going to be of nuclear physics because it was funded by the nuclear science. So we had to pick topics of that caliber of impossibility of competition anywhere in the world and supportable by the Office of Nuclear Science. So with that background, we selected these 3 large areas. So how are the C quarks and gluons and their spins distributed in space and momentum inside the nucleon? And how do the properties of the nucleons, that is mass and spin, emerge as a result of these interactions? How do color quark and gluons and colorless jets interact with nuclear medium in cold nuclear matter? What are the interactions that happen here? How do the confined hadronic states emerge from these quarks and gluons? Then what are the interactions that are also responsible for binding these things together? And last but not the least, what happens to parton densities in nuclear environment? And at extremely high parton densities, where gluon dominates the matter, what are the reasons for it? Is there a universal property, a medium of universal property developed at extremely high energies, universally, no matter which nucleon you look at high energy? So you can look at a proton at extremely high energy and a nucleus at extremely high energy. There shouldn't be any difference from the perspective of the partons. It should be equally highly populated. And this is something, if it exists, would be an interesting thing to look at. Coming to the precision and control, here is the diagram, the Feynman diagram, leading order for electron scattering of the nucleus off of a target. And of course, this community doesn't need too much introduction or details of this. However, what I want to emphasize one thing is that when the virtual photon coming up? Oh yeah, here, okay. The virtual photon is exchanged. And the electron scatters with the scattering energy E prime and an angle theta. Those two things, if you measure them very, very precisely, you basically know the entire kinematics in the collision. And that is shown here. The change in the Q squared, exchange of Q squared, momentum is given by that 4-vector first one. That is the measure of your resolution. And that can be resolved into the initial energy of the electron, the final energy of the electron, and the final angle of the electron. The initial energy of the electron is known because the collider gives us, the machine gives us the precisely within 0.1% the energy. And then depending upon how well you design your detector and how much money you're willing to pay for a very high resolution electromagnetic calorimeter, a well-known technique, you can figure out this Q squared extremely well. Now you go to the next measure of inelasticity, and with the 4 vectors that are here, miraculously, it also boils down to the same 2 variables, same 3 variables. So you can know the inelasticity of the collision very precisely again because of that. And then the X Bjorkane comes out to be the same ratio. The S is the square of the center of mass energy. Again, the collider gives you that very precisely. So now you get everything in terms of E prime, and E and theta prime. And that's the reason why you can do this measurement event by event very, very precisely. If you do this with hadron collisions, you cannot do it because the partons that are part of the interaction will never be revealing their momenta and angles as precisely as we can do here. So you always have that uncertainty that is associated with it. And this works at all energies. This is also an important thing, because if you look at the kinematic reconstruction from LHC and LHC experiments, high energy experiments using jets, etc., they have approached the same resolution. But if you do the same experiment at the region that we want to look at nucleon structure and nuclear structure, those assumptions or those calculations will not work, just because the jet energies are much lower and the precision you lose in that. So this is really what we want to do, and this is what we are trying to do. Now, in the measurement aspect, you can either be very limited in measurement, as I have explained here, but you can be more ambitious by looking at something called the semi-inclusive events, where you look at what comes out of which quark was hit by looking here and then identifying that particle being a pion or a kaon. You can figure out which particle was hit. So you now start getting information about the flavor structure of the collision. And then if you see what comes out as a remnant of the target, you get into the exclusive regime which is where the information, some of the target initial information is moving forward. So in terms of luminosity and acceptance of the detector, you will see that the cost of the detector and the operations demand on the luminosity of the machine goes in that direction. It's easiest to measure the inclusive, most difficult to measure the exclusive. So with that science case that was made, the long-range plan recommended, moving forward, we recommend the high-energy nuclear, high-energy, high-luminosity polarized electron-ion collider as the highest priority. After completion of the FRIP, as people know, FRIP construction is completed and operations started last year in May 2022. And the process of moving forward on the DOE and NSF side with this project had started just before that. As I mentioned to you, with the National Academy. The consensus report said the EIC science was compelling, fundamental, and timely. Timely, not only because the theory had evolved to the level that measurements would be understood in terms of experimental processes, and also accelerator and detector technology was ready to go forward. So the physics was based on these three peers I mentioned before, and we proposed in these documents the luminosity to be high enough, 10 to the 33 to 34, about 100 times to 1,000 times that of Hera, a broad range in center of mass energy, about 20 to 140 GeV, without loss of energy. Most colliders, if you run them at the wrong energy, will not give you the luminosity. Here, we are asking the designers to come up with a design in which you don't lose the luminosity, even if you go to higher or lower, away from the identified ideal luminosity. So that's a very important aspect of this collider. We want polarized beams, electron, proton, light ions, and with flexible spin patterns, a broad range of hadron species from protons to uranium, and up to 2 well-integrated detectors. I mentioned to you the exclusive measurements, which are very difficult to make historically. People have not done that with fixed target experiments, and this is something that we wanted to do very carefully. So we really needed well-integrated, meaning extreme regions of acceptance have also to be part of the physics program. So with that, let me just give you a brief overview of what one could do with such a machine and the core science of essential DOE mission. So the mission, once the project reaches this level, DOE looks at it and says, these are the 3 or 4 things we absolutely need to do. And so they define them based on the report from the National Academy, which was happily identical to the word that we proposed. They didn't have to be that way. They could have missed one. They could have said one is not important or less important. We were lucky to have all 3 of them be part of that program or that argument. So here is the x q squared coverage. Now the momentum and q squared again, of momentum fraction. And here is the fixed target experiments. And these are the regions of center of mass energy range between 22 and 63. The lower side, which comes to about here, that overlaps with the existing measurements, but also goes a little bit further. And this is the highest 45 to 141 GeV that we can do with such a collider with polarized beams. And you can see there are new regions of x and q squared being explored for the protons. Similar thing for the nuclei. These are the fixed target experiments that exist and are about to take data. And then you have regions of unknown q squared and x range where both these colliders, both these operational modes will bring us closer to the gluon distributions. And one thing that one has to remember is that not just taking data in this region is important, but to relate them as functions of x or q squared. So many of these functions that we will be talking about, or many of the structures that we'll be talking about in this regime will have q squared dependence or x dependence. And we want to understand them. So it's not just one or a few points to be measured. And that's where the large luminosity and continuous acceptance of everything that goes into that region that comes into picture. So let me give you an example. A simplest one that is one that I started about 20, 25 years ago. We were measuring things at CERN in a fixed target experiment. We didn't really worry about the angular momenta. This is the delta sigma is the quark's contribution to the proton spin. Delta G is the gluon's contribution. And we didn't know how to even access them at that time, but we wanted to make very precise measurements of that. That comes through a G1 spin structure function, where you take the proton spinning in two different orientations and scatter an electron with a polarized electron off of it. And you look at the difference in the cross sections of this orientation versus that orientation. That gives you access to the quark distribution. And if you make these measurements at different Q squares, then the Q squared evolution of that gives you the gluon contribution to the proton. So these two, we know exactly how to measure and how to calibrate. So what we know now is that in the fixed target regime, there is very less uncertainty. We all agree, all experiments from CERN to SLAC to Brookhaven, everyone agrees. This is what the structure function looks like in this regime. But as soon as you go to low X, there are large uncertainties that come in. And the measurements that EIC could make it possible is shown with these three plots. And then the evolution will be constrained. So the gluon distribution also will be constrained by going to about 10 to the minus 4 in X. And the same is just shown here, where now you show the quarks plus gluon distribution from the high X regime, which will be well constrained as you go to higher and higher center of mass energy from 44 to 141. And you see that the more you measure, that is, the more you go to the low X side, the better the size of the ellipse and uncertainty, where this part is the unknown part, which is coming from the rest of the part. And so you do best with the polarized beams. This is the kind of uncertainty you would get in the end of the program. But it's not just that. These evolutions are calculated using what is standardly known as Altorelli-Parisi equations, but there are other evolutions, BFKL and such, which are more modern, and they exist now. And this is one of the examples from Kochegov, Pitoniak, and Seward, which is a more recent paper that said that the evolution, if there are unusual things going on with the gluon in the low X part, it can go much, much more violently down. I want to compare at 10 to the minus 4. This curve says it's minus 50. At 10 to the minus 4, this curve says it's minus 2.5. So this plot will look something like that on this curve here. So there are very large differences that we can understand, we can try to solve by making very precise measurements in the low X part.
What is the difference? Sorry, what is the difference coming from?
The difference coming from the assumptions of the evolution, the Q squared evolutions of G1.
So coverage
using these dipole, polarized dipole scattering amplitudes and resum powers of 1 over X.
And the other one is just...
It's pure NLO Altorelli-Parisi, based on the best fits that we know today. And then you can look at the same equation again and look at the same uncertainties. And now you look for angular momentum contribution, and you see where angular momentum minus 5, 0.5 to plus 5 will stay in this two-dimensional space. And we will be able to figure out what the total angular momentum might be, not separated, but total angular momentum. If you're building such a machine, we argued that we want to go beyond 1 dimensions. I've already talked about X in Bjorkane, and that's the momentum fraction in the motion, in the direction of the motion of the proton. However, we know that we now have transverse spin effects seen everywhere in proton-proton and transversely polarized proton-proton or transversely polarized electron-proton scattering, which tells you that the transverse structure, the momentum structure, and also position structure has to be in precision experiments try to come in. Fortunately, we now have a formalism called the Wigner function, which is a function of X, which is the same as X Bjorkane. BT is the transverse distance of a parton from the assumed center of the proton, and KT is its transverse momentum distribution, KT in X and Y. So if you do this, looks complicated and never been measured. And of course, KT and BT are two-dimensional objects, so that means it's a 5-dimensional space. But you now know how this connects to the normal one. So if you integrate over BT, what you get is the transverse momentum distribution. We know exactly how to measure it using semi-inclusive deep inelastic scattering. By looking at parton flavor, you understand that very well. If you integrate over the coordinate space, you get into or KT, you get into the coordinate space, which is the distribution of position of that parton within the proton. And then you can get to something called generalized parton distributions, which you can access through such measurements of deeply virtual Compton scattering. I'll tell you what that is. but that's something that we can do. So one tells you about the space coordination, the other tells you about the momentum coordinated, and that will, you can probably just look at, think about it, that R cross P is angular momentum. You can start thinking about it, that we will have access eventually to the parton distribution function. So that's the introduction to this topic. And of course, lattice QCD and other calculations are already making calculations on this front. And so it will be for the first time, you will be able to make, if we can make precise measurements of this, be able to do these measurements and compare them with lattice for the first time. 2+1, so what can be done with this? So semi-inclusive deep inelastic scattering, and here is that electron coming through, scattering off, exchanging a momentum, and then scatters off in this assumed orbitally moving quark that is sitting there. If it hits it here, the effective momentum of that quark after that collision is going to be in that direction. As it leaves the proton, it will pick up an anti-quark and form a pion or a kaon, based on what the flavor of that quark is. So this is the introduction to sort of simple semi-inclusive deep inelastic scattering. And detectors measure this pi plus, pi minus, k plus, k minus, and such. And here is a simulation of such a process using pi pluses with a transversely polarized proton. That means this way for a U quark and a D quark, based on our current knowledge of that function measured from the fixed target. And you can see if the proton is polarized, you can already see that these distributions are not centered. This is what we think will come out with the high resolution spectroscopy. What you can do with it is then to understand why is it that we are going to produce that information with that resolution, looking like an MRI of the proton in the momentum space. Yeah? Similarly, for the transverse position distribution, on the other hand, you have a proton scatters off. So if you want to say something about the internal partonic momentum and position distribution, in the first order, you don't want to destroy it. Because if you destroy it, the position distribution is completely gone. So that's really important to keep that proton intact in the final state and measure it conformably. We have never done that in the past. So, well, recently we have done it in the last 5 years at Jefferson Lab and CERN, but when we were running HERA, we didn't know about this. So what happens is that the photon comes through, the electron is scattered now, it goes inside the proton, it excites a quark, and that quark then emits a real photon to de-excite and be in there, and the proton remains intact. So it's a process of EP goes to E prime, P prime, and gamma, which is a real gamma, and we have to detect it in the detector. And in the past, this proton, which moved very small angle with respect to the incoming direction at HERA, we could never see it. So we really missed this as EP goes to E prime, gamma prime with no result of the proton. It was puzzling for us for a few years, and then only later did we realize that there is this process which takes about 6–7% of the total cross-section. Then we put a detector in front in the very forward region and started seeing the evidence of this proton. Now that we have learned it, but HERA missed the whole physics of that because we had no plans to measure it. Now we know we are better. So now this is the reason why the exclusive measurements become a very important part of the EIC program. And that's why we are planning to do this from the beginning. If the process is resulting in an unbroken proton and a final state vector meson comes in, that's a sign that the initial twiggling happened with the excitement of a gluon. So you get access of the gluon inside. No matter what, these are the kind of things that we want to measure. The transverse momentum distribution can be converted into spatial distribution through a Fourier transform. And you can start getting pictures, again, of position MRIs of the C quarks in a polarized and unpolarized state. Again, using models that we think today might be right, these simulations have been done. In reality, we don't know, but that's the kind of resolution we might get in such things. This is an example of what we have measured in the past, which are puzzling. What is shown on the left side here are RIC results on the single transverse momentum distribution. Asymmetries for pions, pi pluses and pi minuses, red are pi pluses and open blue are pi minuses. And you can see as a function of PT from low PT to high PT, and there are measurements at extremely high PT as well. I just took this as an example, where the pi pluses and pi minuses go in the opposite direction. Left, so these are asymmetries are switched, which means in the previous plot that I showed you here, If the U quark is predominantly charging, responsible for the pi plus, which is going to the left, the D quark seems to be moving in the opposite direction if this model is right. Why that happens, we have to understand. That's not understood. What is puzzling then is to now you look at the kaons, K pluses, K minuses, and both seem to be going in the same direction. Same apparatus, everything the same. Don't understand this. This is a strange quark. It's behaving very strangely here. And these are results that we have known for 20 years and don't understand it. Yeah. So we need to really look at it not only in the momentum. This is only the momentum picture. We want to look at it the distribution with precisely. And the protons left, right don't do anything. It's completely zero. Yeah. So these are the kind of things that we want to look at. These are unsolved mysteries of Rick and previously from PP scattering at fixed target era. But I think to resolve them completely, we need to go to the next level of precision and really understand it. Proton as a three-dimensional object. Let me skip to the last part of that. That is the low X physics in the nuclei. As you can see from the next talk, maybe you will see, we will be talking about low X physics, high parton densities. Ideally, you would want to have what people have talked about in the community, something like an LHEC. Because we try to look for this saturated gluonic object at Hera, and we really don't have a very clear signal for it. So the automatic thing to think about is, yeah, we have to go to higher energy. Of course, you can go. There are proposals people are making. But here we understood that even at lower energy, if you instead replace proton with a nucleus, you can try to get to higher parton densities that you can get with the proton just by the fact that a nucleus is packed with large number of protons and neutrons, which then at high energy look like a soup of cold partonic matter. So that is the idea here, not to go to high energy, but to higher parton density achieved through the nuclei. So this is where we want to go. Again, in the low X, this is log X. We want to go to higher and higher region and see if there is a place where things saturate. And in the region of non-perturbative QCD, we'll be able to calculate this and understand it in a more formal way. To do that, as I mentioned to you, we want to use a nucleus. You boost it, and you look at the entire set of partons coherently with the photon that we have. And then just by geometry and the high energy part, you can get an extra boost of a to the power 1/3 by x. And that's what we are banking on to get to this place. And if you call that as a saturation scale, then the comparison of EP scattering at 300 GeV with Hera, with the nuclei, you get a much higher boost in that saturation scale, and you can start getting regions where we hope we'll be in the more useful state where we can study this. Now, if we are lucky, we will see this very clearly. If we are still unlucky, we'll try our best to figure this out, but this is where the limitations of the machine will be. One of the things that has been mentioned, and this will be done with 2-3 different methods. You will look at FL, longitudinal structure function, where the gluon distribution comes in directly. You will look at F2 of the various nuclei and see how that behaves as a function of the nucleus. But we will also look at things like the density of this object. It has been promoted, calculated, or estimated that this is going to be like a hard, very hard gluonic object, like an opaque object. So you can see diffractive scale minima and maxima if you do electron nucleus scattering. And if it is completely, I think your talk today will have that. One thing that you will see is the diffractive minima. The other thing you could see is that loss of jet. So you can create a electron-proton event where you have 2 jets coming out. And if this idea holds true and the saturation exists, then one of the jets will be absorbed by the high density, and then you'll get a very asymmetric jet system produced, and that would be a signal for it. So it will not be one single result or one single signal that we'll be looking for, but multiple one of them. And we would be able to do this with different nuclei, because this effect should be going away as you go to smaller and smaller size of the nucleus, because you don't have enough parton density in there. You could also get rid of it by keeping the high nucleus, but lower the central mass energy, and then you don't have the coherent scattering as you need. So you have, that's the reason why we need the precision control, dialing nucleus, dialing energy without loss.
Sorry, it's a little fast for me. Why is one jet suppressed?
Because it does. So typically it will be so hard that it will just not be able to get through.
Why not both being suppressed?
It depends upon where they are created. To see, the experimental bias is that so if experimentally we want to see one jet to see the other side. And typically, if the first jet has to be seen, it has to be a peripheral prevent.
So one jet is on the side.
On the side, yeah. Typically, that's what we expect. Yes. Yes, go ahead.
So yeah, I've been seeing this all the time, but one question I have is, for example, the LHC. People have been looking at PA and jet quenching. Right? So in principle, I would think that higher energy in PA, and then this effect
should be the same.
Should be the same, and then the energy at EIC is actually lower.
Lower.
So why would I expect this disappearance? It's almost a jet quenching in the cold nuclear matter.
But the jets are also very much high energetic.
Right. So so I wonder, what do you think?
So my feel, I mean, I can just speculate that we will be more sensitive just because our jets are not that strong. So any impact, any effect of this should be consistent with what you see in the diffractive minima as well as this. So it should be the same effect. But if you have something that overcomes the density, then it will come through.
So you think the jet energy is the key?
I think the jet energy here is key.
But we can also do lower energy jets, let's say P-gold.
Yes, absolutely. If we can do that, that would be great. We should check that. We should definitely do that. Yeah. Last but not the least, the mass.
Just a question. We have been talking about the Coulomb saturation, for a long time. You said that in order to establish the convincing evidence for glass condensate, you need multiple observables or multiple features. I mean, can you give like in your mind, what if we observe something? What is that will convince you we actually have a saturation?
So if you remember, the running of the Alpha S 20 years ago was convincing only after we saw it in different measurements from different facilities and showing all the same consistent behavior of the running of the Alpha S itself. Here, I think we're going to see the evolution of the suppression of the jet as a function of energy that is shown here, the evolution of clarity in the diffractive minima simultaneously, the evolution of F2 structure function, again, based on the same energy scale. You will see that the change in the shape of the F2 will change as a function. The suppression of the F2 will change, and the FL will also have the same thing. So all four of them should be seen simultaneously and a consistent effect. That will tell us, because of the fact that we are on that precarious level of energy, whether it is enough or not, and all these kind of things, I would like to see all four of them where it can, at least 3 or 4, depending upon what the sensitivities are. FL I'm a little concerned about, but these 3 should be giving us the same result.
One of the difference from the Alpha S is that in Alpha S, all the theory predictions were precise, right? I mean, at least in the range of above a few GeV, you actually can calculate them very precisely. Therefore, experimental measurement can confirm the
shows your age. That comment shows your age, Yang.
I know. I just wonder, like, is the theory is well under control for these 4 observables?
No, it is not. And that's why we are launching into a very major effort to do perturbative higher order corrections to these effects. Absolutely. Absolutely. I think people have criticized that. There's one more hand.
Yeah, I have a question, probably super simple. You mentioned that the density of partons changes with the size of the nucleus, and I wonder if you have a simple explanation why.
Well, the first thing is that we are talking about a nucleus which is at a gamma of 100, so it's squeezed, it's like a platform, a pizza, a flat thing, and then as a function of A, more and more of those partons come into picture as the photon looks at them in a certain Bohr cylinder. Does that make sense?
Somewhat. Okay.
Yeah. If you look at the cartoon that maybe I went too far here.
Okay, so let me just go back. But if I look at the nucleus, like just, I guess I cannot just look at it as rest frame because that changes things, doesn't it?
Correct. Yeah, you have to have a high energy probe. Yes.
Yeah.
No matter what you do, you have to have a high energy probe. That's why we want to get to this at the high energy. That's important. There's a 1/x there. That's why this effect is appearing only at the high energies.
Okay, but like, okay, in terms of, I guess some simple upper level or higher level observables, like you still think you're probing the nucleus at saturation density, or do you think you're going to probe the nucleus at something else?
We don't know that. We are hoping that it will be the saturation density.
Ah, okay.
Yeah, because as I said, ideally you want to go to highest possible energy to look at this, just experimentally. Yeah, you want to go to the highest possible. This is what is possible, we think, for $3 trillion. $3 billion.
Thanks.
Would be nice.
1,000. I just lost my job. Okay, very good. All right. So similar to the sum rules for a proton spin, there are some rules that have been proposed as the mass spin rules, where parts of the total energy associated with quarks, gluons, and quark mass, fundamental from chiral symmetry breaking, come into picture. And then there is something called the trace anomaly, which is the gluon effect, which comes only because of the gluonic interactions. Many of them are measured indirectly in experiments and in lattice QCD, and those are possible, but the largest uncertainty seem to remain in the trace anomaly, which then remains as an unknown thing from the experiment as well as the theory side. And to understand the proton mass, we were told in various workshops that we had that the 25%, off the order of 25%, which is estimated from the lattice QCD, it remains rather difficult to measure. There are ways to do this with some, again, this is a new thing, experimentally addressing it is an ongoing process of understanding how best to do that between the theorists and the experimentalists, but a threshold production of J psi and upsilon in such a deep inelastic scattering such a thing can be possible. You're looking at cross sections on the verge where the J psi and upsilon are produced without any momentum, and then in that frame they look at the decay of that, and from there you can get to this place. The current experimental measurement of GlueX at Jefferson Lab is shown here, and possibilities with a future experimental proposal at Jefferson Lab called solid experiment, where it will do the J psi measurement, is shown with that. And at a higher energy with the collider, these are 3W bins in which these measurements seem to be possible. What is assumed here is that the ratio of, in this flat line is assumed 25%. That is the estimate that seems to be coming for these anomalous or the anomaly to the total proton momentum. So this would be a measurement that is needed to understand the proton mass in the big picture. And it looks to be possible if all the theoretical aspects remain as we expect to be today. I want to summarize and go to the next part of the talk. What is shown here is the center of mass energy on the x-axis and the luminosity per centimeter per second per centimeter squared, the instantaneous luminosity on the y-axis. On the x-axis, on the y-axis on the right is integrated luminosity, assuming the luminosities, the running times of RIC that we have historically experienced. So at 10 to the 33 luminosity, in 1 year operation, we will probably get 1 inverse femtobarn. At 10 to the 33, an operation will give us, a typical year's operation will give us 10 inverse femtobarn. And then this will give us 100 inverse femtobarns. Most of the physics program that I mentioned to you will be covered with multiple years of running this, and in fact will be a lot more luminosity than we can really need. It will be a systematically controlled or limited experimental measurement. The nuclear landscape do not require large luminosity. It can start very quickly over a large range in center of mass energy, but you can start looking at nuclear internal structure The extreme parton densities of saturation will need the highest possible center of mass energy to go to 140 GeV. The spin structure will require, flavor structure will require higher luminosity, and the tomography and the mass will require even higher. So those are the kind of pictures that we can draw based on the science and the luminosities that are needed. All right, so now let me give you, after this, when this was blessed by the National Academy, and this is where the EIC project was formed, and the DOE took it over. Now, it's a partnership between Brookhaven and Jefferson Lab. As I told you, there was a friendly competition to start with. I think the competition helped both sides to improve their designs overall, but eventually the cost considerations of realization made the solution to Brookhaven. Eventually, these two are now running in together and building the collider as partners. This includes, the project includes the accelerator complex, the full accelerator, one interaction region, and most of the first detector. It's important that now I'm getting into the big picture. While we do this, we have to be absolutely sure, because of the complexities of the collider. I mean, I always feel, and the accelerator physicists agree, it is one of the most complicated machines ever built, because we have really asked for too many things at the extreme of the knowledge of accelerator operations. We want the collider to have polarized electrons. We want the electrons, the protons, and three-dimensional, with different orientations, transverse as well as longitudinal. We want the hadrons and light ions to be polarized. We also want them to be rotated transversely as longitudinally. We want nuclei of all varieties, from proton to uranium. And then we want all of these things to run at different energies without significant loss in luminosity. So this puts a lot of pressure on the accelerator folks. So they started very early to design one IR and how to integrate that detector, the first detector, into the IR. Because to high luminosity requires focusing magnets that come too close to the magnet, to the detector or center point. And then the detector needs to have large areas or large lengths to see all the things that are happening in the collision. So these by itself are contradictory, but they need to be making compromises. And you'll see how that has been laid out. Machine elements come very close, become part of the detector, and detector components become interspaced in the machine elements as we go through the ring. And also, while we do this, we have to make sure that the second IR, the possibility of the second IR, is not destroyed. Because with the kind of focus that you need on the first detector and the IR, you are easy to make a design in which there is no way to collide at another place, although there is a space for it. So this has to be always in the mind. So there is a precarious balance of all these requirements. I don't want to spend too much time, but this is the whole project that has been set up. As you can see, the lab directors are in the driving position here. This is the real project. This is led by Jim Yeck and Ferdinand Willica and Kevin Smith. And then there are people from Brookhaven and Jefferson Lab, which are in charge of the detector and all the accelerator and other management positions. And then there are peripheral committees. I will not go into too many details, but there is technical peripheral committee. There is the Office of Director of EIC Science. Then the user group and the EPIC collaboration now set up. Then the advisory committees to the project and the advisory committees at the highest level to the director themselves. So all of this has come through, has been working for the last 2 years. Through the pandemic was set up. And you can see the distribution of responsibilities is where the leading technology and experience for each lab is. Here's a little bit of a close-up of the top part, and you can look at it. But BNL with Brookhaven and Jefferson Lab envisions EIC as a fully international facility. There is advisory group, provides oversight and advice to the construction of the facility, focusing on the accelerator, and various people and expertise from various international labs are already involved. The project advisory committee provides delivery, is responsible for advising towards successful delivery. And that gives management, scope, schedule, cost, and performance, and a RRB, which is the Resource Review Board, to provide oversight with the detector, which is very similar to what CERN has set up. So we have taken a lot of things from the European projects, large projects, to set it up really like the international project. Here is what the machine will look like. This is the overview. The injection system is the same. Booster, polarized sources, and unpolarized sources. AGS gets into the RIC, gets into the red ring here, which is shown there. That is actually the yellow ring of the collider, if you know what I mean. There is the first detector will sit here. A potential future second detector will sit here. The electron cooling sinks here. Line injection is there, and you can see that the electron will go in the other direction, inject into this blue ring, and then collide at IP6, which is the current location of the star and the future location of the epic detector. And then possibly in near future, beyond that point, there will be a second collider detector designed and installed in the IP8, 8 o'clock of that dial. These are the same parameters that I'm telling you. The current knowledge of the machine tells us that we will reach luminosities of this kind, which are shown by this broad band. And there is current effort going on to improve the luminosity even at the lower center of mass energy to higher energies, higher luminosities, which currently is limited by mostly how cooled the beam is. And so we are trying to we can do low energy cooling. We might be able to get to that place. So you can see that no matter what, the whole science of EIC will be covered by that luminosity that I mentioned to you before. That requires a lot of upgrades and changes. So the hadron ring is the same. We just need to go to much higher beam currents. It's about 3 times the RIC. Currently, we have about 100 bunches. We have to go to 1,000 bunches, 1,160. We have 96 nanoseconds between bunches right now with polarized or different polarizations. When we reach the EIC operations, we want to get to 1,500 to 60. That's the maximum that we think about. That will bring the interaction frequency to about 12 nanoseconds, so 9 nanoseconds, which means that the detectors have to be designed appropriately to be ready for bunches at that frequency. The electron storage ring is completely new. The rapid cycling synchrotron is completely new, and the interaction regions are designed to be completely new. The default one, the IP6 location, has to have a crossing angle. I mean, both of these will have a crossing angle. Because the protons bunches are seeing each other that frequently, you cannot have a beam that goes straight through, because then all the bunches in the full interaction region, the straight beam pipe, will start colliding with each other. And then you have a mess outside and inside the detector. You'll have collisions everywhere in that region. So you have to have a crossing angle. To get to high luminosity, we're required to do this, but then we have to have mitigating instruments to do that. So this is the current look inside the tunnel. After the tunnel, this artist design looks like that. We'll have one ring, that's the yellow, and then this second ring will be replaced by the electron facility, the electron booster and the electron ring. So how do we get to the high luminosity? So luminosity is always a benefit. We are all experimentalists. We want it, the theorists also want it. So you want to first instinct is to maximize the beam current. The luminosity benefits from reducing hadron emittance by cooling. If you have a very broad beam of 2 beams colliding, then the luminosity is by definition low, because the probability of one hitting the other in a very broad cloud of protons is going to be small. So you want to focus them. You want to bring them very, very tight. That's called the cooling, not only in the transverse direction, but the vertical direction as well, or the Z direction as well. So that's called cooling, and that's the instinct. Minimizing the number of bunches, meaning that you want to get to the highest intensity in each of those bunches and then minimize the number of bunches in the ring. If you don't do that, you can get to, you require 3,000 bunches, which will be impossible to handle, because now the bunch frequency is every 2 seconds. Even a beam crossing that we installed will not work. So that's the balance that we have to do to reduce on demand the beam cooling. The detector is friendly. It is detector friendly because 12 nanoseconds is better than 2 nanoseconds. And the results of the small beam divergence also comes into picture. So here is the list. And one of the things that, I told you that we need to come up with ideas, 12 nanosecond bunch spacing with 25 millirad angle. We need superconducting final focus magnets, spin rotators, large acceptance, forward acceptance. But we also need something called crab cavities. The crossing angle, you can see that here's a, let me see if this works. Yes. So we have now a 25 millirad crossing angle, the electron beam coming from there, ion beam coming from there. And you can see on the overlap, the bunches are crossed like this, which means that they're not interacting. Ideally, you want to have this kind of full bunch crossing to have the maximum luminosity. But because you made the bunch crossing small, you were forced to go into the angle, and back because of the angle, you now have reduced your luminosity again. So what you need is a magnet called a crab magnet that sits here and there and there and there, that turns the beam over just before the collision. That is a picture of such a magnet, a crab. And now that is changing the orientation. You can see that this comes in, then goes in, and here point, now there's a full bunch cross. And this is showing the full overlap, so about 90%. This never goes beyond 40%. That's something that has never been done for hadron beams. It has been done for electron beams at KK. It does not work perfectly, but I believe in super KK, it will work, yes.
One thing that's always puzzled me about this cartoon is so it goes through the crab cavity, it gets a kick,
yeah,
and it starts rotating,
yeah,
but then it bounces back and starts rotating the other direction.
Yeah.
What's causing that oscillation?
Because of the fields here.
Okay.
Yeah, it will start. It's not an instantaneous kick. It is a slow change, and then it has to come out. It just creates an oscillation. So if you don't have this one, it will keep on oscillating like this going through. Yeah, and the solution, the resolution. You see that here? So the red is the electron bunch, and the blue is the hadron bunch. And you need to make as best a match as possible. If you don't, you create a situation like this, in which now there is a lot of positive charge around a negative charge. And that's destructive, because this will then shrink further. Just the electrons around the protons around the electrons will shrink that first, and that will be detrimental to the entire collision again. So that will destroy the other beam again for the next collision. So there's so many things that are new here that need to be pushed and being.
Any significant energy loss from bending the beam on such a small scale?
The beam is not bending. It's the bunch is being twisted and brought back.
Ah.
Okay. So bending of beams, we lost huge amount of time at Hera. We used to have an electron beam that comes through and collide and go down. And there's a simple, straightforward arc. That means that the whole transition from this angle to that angle created a plane of synchrotron radiation, which we could not handle when we upgraded the luminosity of the electron bunch in 2001. We learned a huge lesson there. So in this case, the electron bends about 50 meters away from the IR, and it's just a straight section that goes through until the IR. No bending of the electron bunch. And the proton doesn't synchrotron radiate, so it's not a problem. But this is just a term. Now, there will be issues with small amounts of changes kicks in the synchrotron radiation that will happen here. But they're very small as far as we know from these solutions, these simulations. So this crabbing is another push towards novelty in accelerated science and challenging project. This is what IR looks like.
Sorry, what's the scale there when this starts with a kick from the
distance from distance of the crab magnet?
Yeah.
I think it's about 20 meters. 20 meters just behind the ZDCs. ZDCs are 18 meters, right? Correct?
28.
28. So it's just behind that, so it's 30 meters. Okay, now we have to build a detector. Now the machine is getting in space. Now we have to build a detector. First, we need people. So that's what we started with the user group. We started with about 400 people in 2016, just after the long range plan approved it. And you can see it has grown very significantly to about 1,400 people right now. And it covers all the entire world in terms of doing these experiments. You should not be surprised by that. Many of these people were doing experiments at CERN or SLAC or at Brookhaven or at PSI or in Japan, trying to understand nucleon spin in different ways. So we all have reached the level where, say, we all agree that we need to go to lower X. We all agree we have to go to high Q squared. We all agree that we need high light nuclei to understand some of the nuclear problems. So it is not surprising that we have a broad support, and that is reflected on leadership taken for all the user group activities. And we have, gone everywhere. We tried to do one in the country, one outside, and we are going this year to Warsaw. Last year, we were supposed to be in Warsaw last year, but because of obvious reasons, we couldn't go there for 21, 22. But finally, we are going there this year. And this is the composition, and it's truly, truly international. You can see that the North American component is about 20, or this is the 30%, I think. The Asians are 25%, the Europeans are about 30. So you can see that it is really, sorry, this is this color right here, 40% local and 60% more from outside North America. So it's really an international organization that has been formed. When more people come in and the collider takes a lot more seriously of shape, we want to go out and see what else can it be done. Now, this was not part of the, as I mentioned to you in the beginning, not part of the core case because the nuclear science had to be approving this collider. But obviously we knew that there would be other things that we could do with it. And here are some of the interests that were captured by this year's and past year's SNOMAS study for the high energy physics. And you can see that there were studies of various things of unpolarized PDFs at high X and high Q squared, which are required input to the precision future studies at LHC. Precision high precision calculation of alpha S. You can study this from various things, but particularly about jets, from doing higher order corrections to see the spreads of jets at energies, different energies, and how that changes as a function of center of mass energy. Also from spin structure of the proton, you can study alpha S. So all of these are coming into picture. We have just started activities on quarks and quarkonia, with now people looking at what could be done with physics, what physics could be achieved with 10 to 100 times more luminosity, polarized night nuclei, nuclear targets. We have seen in the last 5 years, absolutely fantastic results from LHCb about quarkonia, 4, 5, multi-quark systems. Again, precision QCD with jets as a probe, but also structure of jets has evolved into a group that is working on that. And last but not the least, which is the beyond the standard model physics, which is a precision electroweak science to look at lower energy impact with high luminosity, but with precise measurements of lepton flavor violation, charge symmetry, parity, etc. So I think there is a group that has now started to work on these kind of symmetries with input from high energy physics as well as nuclear physics. And I think a lot of the QCD objects I mentioned to you before, partons don't distinguish between what the initial state of the collision was. They do what they have to do, and we need to understand them in different ways. And that's really the universality study that comes through different types of measurements. Here is that paper that came out, a summary of the SNOMAS. And just one place summary, what I want to point out is that the topics are what I mentioned to you, the interest from the high energy physics is understandably different. And that is reflected in the sequential studies that they presented in that paper, which I think is consistent with what we wanted to do, at least in a few places, but the sequence seems to be different. So I think this is going to grow. Hopefully there will be a lot more high energy physicists coming to work with us in the same way. People from our field are now getting involved with activities that are going on in high energy as a result of those collaborations that have evolved. Let me go to the last part. I'm quite far. How far am I? Okay, I'll go faster now. But there were questions, so I'll tell you a story afterwards. Overrunning. So anyway, a detector, central detector. This is going to be faster because these are some facts. So central detector is an asymmetric collision. You need the hadron side going hadron end cap, what we call it. We have a special detector on this side, particle identification and time of flight with calorimetry, electromagnetic as well as hadronic. On the other side, we don't need as much, but we need precision lepton measurement on one side to do all the inclusive, make sure that the purity of the event is extremely high. If you want to really do leptoquark, I mean, the inclusive studies in the particle physics region, that region is extremely important to make sure that there are no misidentification of pions, even at high energy pions, electrons, et cetera, et cetera. So you can see that that's the kind of scattering design that we start with, that we did over that period of stay at home during the pandemic. We came up with a design that looked like an ideal detector. And this is the particle identification and hadronic side. That's the electromagnetic side. And you had HCal and EMCal all around with tracking in the center. Time projection chamber was proposed at that time. Particle identification with time of flight, etc., was also part of the original decision. From this idea started the construct of proposals They were asked to come up with with proposals, and there were 3 proposals made by the community, out of which one was selected, which was at that time based on the existing S-Phoenix magnet and built around it using some aspects of that. We have now formed that. So sorry, again, want to emphasize one thing. This is the central detector dimension. And because of the exclusive measurement that you want to do, you want to insert detector magnets all the way down into the beam line. This is the hadronic side. You can see the off momentum detectors, Roman parts that go all the way to about 40 meters. On that side, the electron scattering, you want to have tagging for electrons for measurement of electron luminosity, et cetera, So the detector components go all the way to about 30 meters on both sides. So this is only the central part, and then there is the early part of the machine and the further part. So that's really what the complication of creating a detector to do exclusive measurement looks like. The design that came up, which at that time was called HA, that became Athena with a combination of, it became EPIC with a combination of Athena as well as HA together. And we have formed the first collaboration. We just finished our management first elections. Jean Lajoie from Iowa State and Sylvia Della Torre from INFM Trieste have been elected as the first spokespeople. And the detector, again, looks very similar to the ideal detector design that we proposed, with the particle tracking in the center, followed by particle identification, followed by the calorimetry and the hadron calorimetry. They have been laid out in the interaction region as given and optimized, and we know how they will fit in the interaction region, et cetera, and how they will perform. Now going back to the physics, people are doing simulations, detailed simulations with this final design now to get to the real detector. So there's the physics that will evolve, and the process of finalizing that detector, and contributions from various countries has now started. So that's the first interaction region. I want to spend a couple of minutes on the second interaction region. There are fundamental differences. If you see carefully what the yellow ring does from going from left to right, it goes from inside to outside in this region. The electron goes from outside to inside. In this interaction region, it's the opposite. The yellow ring goes from outside to inside, whereas the electron goes from inside to outside. Now you can see that the magnets that are needed to control the beams are different sizes because they are very different rigidities. One is superconducting, one is non-conducting, which means that the physical space available around the interaction region becomes an extremely important idea. Because if you bring in the wall of the tunnel on this side very close, then this prohibits you from putting a big magnet on this side. And that's why having electron beam here, which is a smaller control magnet, works better here, whereas there is more space on this side to control the electron, the hadron beam, and vice versa here. So those are the kind of things that come into designs. They allow us to have different crossing angles. So for example, this one is 25 milliradian. We're thinking of having the second at a different angle. Currently between 35 to 40 is being considered. More like 35 will be possible. Because of that, then you can have longer focusing areas. And so you can have something called a secondary focus that goes a little bit further down in that direction. There are different blind spots that are doublets. The magnets are different. We have evolved from the original idea of about 1.5 to about 1.7. We're building a new magnet for the first IR. We have to decide what to do with the second IR. We really want to go to 3 Tesla or something different, lower, not higher probably, just because of the risks involved in building a new magnet. But those are the kind of discussions that are now coming through. The tunnel size I mentioned to be slightly different on both interaction regions. And so all of those then have to evolve into a coherent package of the second IR. I think I've said everything in this plot. This has also been laid out to some extent with no detector details. You can see the blue block is there. Look at the interaction region, what is spent, what is available on the right. What I want to show is what is the possibility, one of the possibilities, and I think Barak Shmukler talked about it in week 2 in this workshop, so I'll not give. I picked one slide from here. What is shown here is the exposition at the Roman part 1, which was the far, far away detector that was sitting in the beam. And you can see that there is the blind spot for the detector is shown here, and the nuclear fragments, which are from a nuclear fragmentation process in EA collision, are shown here. So if this is my blind spot and this is what is being created, then you are able not to see all of these. So you're going to miss all of that physics if you really are interested in that physics. For the second IR, if you build this second focus, which I said, longer term thing, then that blind spot can be reduced quite significantly because of the space available there and the geometry has been set up. And the x-axis of these two is the same. And you can see that the blind spot is very small. So you can do a lot more. So the hope is that these kind of ideas, this is not the only thing that will dictate it, but these kind of ideas are needed to see what complementary science one can do. And this particular study, for those who are doing lower energy nuclear study, nuclear physics, was done for identifying exotic nuclear objects when you do EA scattering. So short-lived nuclear radioactive isotopes, which you could not see because they are so short-lived in the lower energy FRIB or FRIB-F, we think we can identify them, we can look at them if we have the acceptance possible like this. And because, remember, they are boosted by gamma of 100, so they live longer, so they're easier to detect. So that's the kind of thing that we're looking for to make connections to other things. So those are the considerations. It's not in the object project. Challenging parameters for the IC requires the attention post second IR. The design has to be done now for both of them not to negate the possibility. And so this is the activity which is now led by, again, user group. What is the compelling physics for second IR? What's the balance between physics and affirming the core physics with compared to detector one? Complementary technologies, generic R&D that is needed to get there needs to be supported by such complementary technologies. And then we have to go back to the timeline, etc. Last 3 slides. We are going through the process of realizing the EIC. We're somewhere here. There is critical decision 0 was done, 1 was done. We are past CD1. We're preparing for CD2 and CD3, which will happen in the next 1.5 years. The final design has to be there at the CD3, which is where the construction starts. And I'll give you small timelines for that. Funding-wise, this is the expected funding. You can see that's the growth of the funding. This is the saturated part of the funding. And then it will come back to 0 when the construction is complete, somewhere between FY23 and 32 and 33. This is the IRA, the recent boost that we got, and that really made us happy that we have now money, essentially what we would have expected to be at the beginning of 2024. So all the drawbacks of the first 2 years of not getting enough was filled by this and more to take us into the 24 operating funds. Construction funds. So we were very lucky to have this, and I think this has really saved us, put us back on the same timeline, and now we will go into the timelines of that. That's my last slide. You can see where we are, CD2, CD3, that's we are expecting somewhere around January 2024 to some range in the next 3-4 months. CD3 approval is expected in 25. That's what we are planning for from the construction side. All these things for the infrastructure, the accelerator system, and the detector are being planned with those things in mind. And that will lay out a early collision criteria called CD4A, somewhere between 31 and 32. This collision will not be the for physics, but for only machine operations and optimization. That will be the dictating fact. Once they are happy, the machine physicists are happy, that's when the CD4 will happen, which is where the detector has to be fully ready. Here we have to be ready to give them enough feedback to optimize them. Here we have to be ready in the light part to ready to start physics. So somewhere in this region will be the start of the physics, where this is the first collision. So there is and then on that, the second detector will go about 3 to 5 years later. And hopefully, once this is almost ready, we will start the early commissioning part of the second detector. All right. It's an international project. There is a lot of interest in building things internationally, and both DOE and international funding agencies are working together at this stage. This has come a long way. I showed you the last 5 years, but those plots are from 1996 in various white papers. These are from 2004, 2000. And then it was started as a project to be done at Hera. So the top parts are at Hera, polarized Hera and nuclei. And then when that didn't seem to happen, we all came to the other side of the pond and started this effort. And so finally, we are where we are now. So that brings me to a summary. So high energy, high luminosity, polarized collider will be built and will operate through 30s and probably 40s. I will address some of the most profound unanswered questions in QCD and hopefully will give us more puzzles. It's an international project, both on accelerator and detector. The timeline is aggressive, we all agree. The detector is hermetic. Two need to be built eventually. Hopefully, they will be complementary in many different ways. How different, we don't know yet. That's to be decided by users and doing physics studies like this. And we'll need substantial yet unidentified funding for the second detector from non-DOE sources. There is high international support. And for young physicists getting into the field, this is a machine that they will inherit and do physics with. Thank you very much.
Very much.
Sorry.
Other questions?
Yeah, for the differential process, for if you are coherent and incoherent perceptions, and
We will talk about it today.
And the coherent, you have very beautiful patterns. And how many minimum do you expect to observe in EIC?
I hope to see 2 at least. Will you agree?
Expected 3?
3.
Yeah.
3 minimum.
Yeah.
And also, can you disentangle the coherent and incoherent?
We have to. There is no chance
Yeah.
without seeing it, so we have to. That's something we have to work very hard on. But you will discuss this today, right? Or tomorrow or whatever.
Friday.
Friday. Okay. More detail you'll hear about
Okay,
that.
thank you. May I ask one more question? Yeah, for the EP, EA, and PPP, for hierarchy, for A or even P or even PP, yeah, collectivity. And recently, the UPC, you also observe the collectivity. Do you expect the same behavior in your EIC?
If UPC has seen it, I would be willing to bet you will see it.
But UPC, you have to reach a high
I
mark.
know. But yeah, there are people, my heavy ion physics friends tell me that they should be there.
So you expect also similar collectivity?
Yeah, I think at the fundamental in this process, EA, looking at the gluonic object what is the actual interaction going on? It's not the electron that is hitting as a point particle. It radiates the photon. That at high energy becomes a quark-antiquark pair, and that goes through the nucleus. That's where the interactions in the strong interaction is happening. So if you have 2 objects going through the nucleus, there is always a chance you will start seeing collectivity, exactly like the deuteron going through the nucleus, right? At a different scale, but the same thing.
You have to go to high mark distribution. I mean, you have enough final.
That's detailed. Yes, I agree. Yes, sure. So yes, it would be interesting to see it. I don't know whether I will see it, but it will be interesting to see it.
So I think we'll having much higher multiplicities. The reason is, of course, we have higher luminosities. Energy might not be as high, but then we have the handles on the Q square. So for example, if we believe the physics universal, then doing photo production will be exactly like
that, yeah.
And then the question will be, what if you're going to DIS measurement, right? We think so. I don't think observing the same thing will be a surprise.
Okay.
I think more question to you guys is how to understand it.
So it's a naive question. How many particles are we talking about being produced?
So if you look at Atlas, this multiplicity distribution can go up to, it's like a negative binomial distribution. It can go up to, let's say, 40 tracks, 50 tracks. And then in the EIC, I believe it can also
go to that.
One more, one unrealistic question. Do you expect this energy loss when highly parton go to 3DC matter, such as similar to the highly parton go to quantum plasma, the energy loss? Is there any similar phenomenon?
So the only thing I know, yeah, I mean, there should be, of course, but not necessarily in the, if you have a perfect CGC, then it will be difficult to go through it. I mean, it would be very hard. But nuclear DIS, we expect to see energy loss. We expect to see studies of light quarks versus heavy quarks going through cold nuclear matter.
Yeah, but somebody had estimated that the Q hat of the interaction between the proton and nuclear matter is very small, but the Q hat of the proton and CGC is very large.
That I don't know this calculated estimation, but I'd be happy to.
But
Do you know anyone?
What is your question?
I mean, do you expect to observe the energy loss when the high proton comes from CGC matter?
Well,
I mean, first of all, we already observed at the lower energy, Hermes, you see a large suppression, cold-nuclear matter effect.
Yeah, this is cold-nuclear.
Right, so he's talking about
CGC matter.
prove that there is CGC, but CGC is a loss of energy, the total loss of energy.
So I think, for example, depending on what kind of observables, but recently, like at RIC, we do observe something along this line, right? We have dihedral correlations, and then we see the disappearance of angular correlations. This is one of the observables. And then I think if you're talking about like quantitatively in the CGC framework, I'm not sure there have been calculations.
Yeah, that's I'm not aware of that.
Okay.
But
you said there is an estimate of Q hat, and
yeah,
we'll see. I'm not aware of that.
yeah, okay, sure.
Any other questions? No, so thanks again.
All right.
Take a 15-minute break. Come back at 10:40.